In this first video for Chapter 5, we're going to begin to look at the idea of probability, and we're going to expand this idea in future chapters. For the most part in this chapter, we're going to focus on calculating theoretical probabilities, using theory to make these calculations. There is another type of probability that we'll discuss briefly, empirical or experimental probability. That's when you physically carry out an experiment. You actually flip a coin or spin a wheel or something to that effect. But for the most part, we're going to rely upon theoretical probabilities. When we rely upon theoretical probabilities, we look at the sample space, which is just all of your possible outcomes. So, for example, if you're rolling a die, the sample space would be the numbers 1, 2, 3, 4, 5, and 6. That's all you could get when you roll a single die. And so that sample space would be small, and the outcomes, those numbers are equally likely. I could list those out, and it would be helpful in making my calculations. When there are many possible outcomes, we're not going to worry so much about the rules of probability. Instead, we'll just use what we know and some theory to make our calculations. Generally, what I say is if you have 40 or more outcomes in the sample space, that's too many to list everything. We just use theory there. But if it's less than 40, it is possible to list the sample space in a reasonable time and to make some calculations from there. In addition to sample space, another term to focus on in this video is the complement. And we'll call the complement the not event. It's the opposite of a particular event. For example, the complement of it will rain is that it will not rain. If there is a 70% chance that it's going to rain today, that means there's a 30% chance that it will not rain today. For notation, we've got this AC that's going to denote the complement. And note that the probability of an event A, this P and then the parentheses denotes probability, so the probability of A plus the probability of the complement of A is always equal to 1 or 100%. That's a characteristic of complements. They always equal to 1 or 100%. That's how I knew if it's a 70% chance that it will rain today, then there's a 30% chance that it will not rain because those add to be 100. You could also derive from a little bit of algebra that the probability of A's complement is equal to 1 minus the probability of A. You could say 100% minus 70%. That would give you that 30%. Example 1, we're going to use a deck of cards to examine the sample space. Example 1 says, consider a regular deck of 52 playing cards that have been shuffled. What is the probability of drawing a red card? Probability of drawing a red card would be 26 out of 52, which is equal to 1/2 as a simplified fraction or 0.5 as a decimal. And let me show you quickly in the calculator that you can get that decimal either way. If you take 26, divide it by 52, you get 0.5, or if you take 1 and divide it by 2, that also gives you that 0.5. It's always the numerator divided by the denominator. And before I move on to parts B, C, and D, I know that not everybody is familiar with a deck of cards. So just to break that down on the side here, to begin with, there are 4 suits. There are hearts, which are red cards. There are diamonds, which are red cards. And then there are spades and clubs, which are black cards. And there are 13 in each of these suits. There are 13 hearts, 13 diamonds, 13 spades, and 13 clubs. If you add all of these 13s together, that gives you 52 total. So that's how I knew this probability would be 26, the 13 and the 13 here, make 26, divided by the 52 total, gives me my probability. Also of note, so there are 4 of each type of card. There are 4 aces, there are 4 kings, there are 4 queens, and this keeps going. There are 4 jacks, 4 tens, 4 nines, 4 eights, all the way down to 4 twos is the lowest you could go. There's 1 in each suit. There's an ace that's a heart, an ace that's a diamond, an ace that's a spade, and an ace that's a club. To look at part B, what is the probability of drawing a card that is a diamond? Well, there are 13 diamonds according to my list, so I could say 13, and we're always going to divide that by the total in the sample space unless we have a conditional probability, which we'll see later on. This simplifies to be 1/4, which as a decimal is 0.25, and again you can check that either way. I'll just go with the 13 divided by 52. Your homework is going to vary in how it wants its answers. Some will be asked for in fraction form, other answers will be asked for in decimal form. For C, the probability of drawing an ace, I've already listed that there are 4 aces out of 52. That's 1 out of 13. Take that 1, divide it by 13. If I round that to 4 decimal places, that's 0.0769. You could also list these out as percentages. 0.5 is the same as 50%. 0.25 is the same as 25%. And we could say that this is 7.69%. Finally, in D, what is the probability the card is not an ace? So it could be a king, could be a queen, could be a 2 or a 4. There are 2 ways to approach that. One way is to total the number of cards that aren't aces. If there are 4 cards that are aces out of 52, that leaves 48 out of 52 that are not aces. There are 48 cards left in the deck. This is the same as 12 out of 13. And if we divide 12 by 13, we get 0.9231 if we round to 4 places, or 92.31%. Note that C and D are also complements. Probability of drawing an ace versus the probability of drawing a card that is not an ace. It's the not event. So these 2 probabilities should add to be 100%. If you take your 100%, subtract the 7.69% from before, that also gives you 92.31% as a second way to get the answer for this problem.